Okay, so this video is going to go over the sine law, and so what the sine law does is it takes side lengths of a triangle and then relates them to the sinusoidal function of vertices angles. So as we can see by the sine law here, it's a over sine A is equal to b over sine b, which is equal to c over sine c. And these equivalencies also hold in the case where we take the reciprocal and have the sinusoidal function in the numerator and then the side length in the denominator. So let's see if we can solve for missing sides, missing angles, or sometimes a little bit of both, just depending on the problem, using the sine law. So when we take a look at example 1 here, it says determine the side length of AB. So the side length of AB is actually just denoted by the length that is between A and B. That should be pretty straightforward. Anytime we see two letters next to each other like that, it's always going to be the line that connects those 2 points, or those 2 vertices. So in order to use the sine law, though, we have to use a known side and angle and another one in order to get that. So let's start by labeling, just using our little letters that symbolize our sides. So across from the A vertices, we're always going to have our A side. Across from the B vertices, we're always going to have our B side. And across from the C vertices, we're going to have our C length. So technically what we're doing by determining the side length AB, we're solving for C. So in order to use the sine law and use it effectively in this case, we're going to have to use what looks like B and C. So let's write this out in a way, because we can technically write it in either or fashion. So we can either write the side length in the numerator or the sinusoidal vertex angle in the numerator. Let's select the one that we need for this case. So if we know we're solving for side length C, let's write the side lengths in the numerator. So according to sine law, we have C over sine C is equal to B over sine B. Now let's fill in the information we do know. We don't know C, we don't know sine C because we don't know the angle of C, but we do know side length B, and we do know the angle at B, which is 88 degrees. So in order to get that sine C, or the C angle specifically, we have to remember that the inner angles of a triangle are always going to sum up to 180 degrees. So off to the side here, we can say 180 degrees should be equal to 88 degrees plus 35 degrees plus C, whatever that C angle is, or the angle that's specifically right here. And so going into our calculator, what we would have to do is we're going to have to subtract both the 88 degrees and the 35 degrees from this side and this side. Thus, we're going to isolate C as 57 degrees. So now we can write in 57 degrees for our angle C. Now we have all the information we need. We just have to sub it back in here for our equation and solve for C, because that's the side length AB we're looking for. So C over sine 57 degrees is equal to 44 over sine 88 degrees. And what we have to do to get C alone is multiply both sides by sine 57 degrees. And that's going to end up canceling the sine 57 out of the bottom, but multiply it to the other side. So we get the side length C, which is also equal to AB, equal to 44 sine 57 over sine 88. And that is equal to 36.9. And we're going to use the units of measurement, which we have over here, which is millimeters. So we can actually just write this in as 36.9 millimeters, and that's rounded to the nearest tenth. And then we can also write it over here on our triangle because that was the side we were solving for. Now, what do we put example 2 here? Example 2 says determine the marked unknown angle. So what we're looking for is we're trying to solve for this angle here, angle A, because that's our marked unknown angle. So if we want to consider the proper sine law function, what we're going to have to do is we're going to have to say, okay, well, what sides do we know, and then what angles can we use here? So it looks like we know for B, we know both the angle and we know the side length. And for A, we know the side length, but we need the angle. So what I'm going to do is, if we know we need the angle, let's write, if we go back to up to our first page here, we can see that we can write these fractions or these ratios in either order. I'm going to write it so that our sine function is in the numerator, just to save us steps of manipulating these equations. So specifically, we're going to use sine, let's use sine A over A is equal to sine B over B. And now let's fill in the information we know. So we're solving for the angle A, so we don't know that yet. So we can write sine A again over A, which was 15, is equal to sine B. Well, the angle at B was just 98. And then over its side length, which was 17.5. Now to rearrange this, what we have to do is we have to multiply both sides by the 15 that's in the denominator on the other side. So that's going to help us eliminate this 15. And now we're just left with sine A is equal to 15 sine 98 degrees over 17.5. And then to get A alone, we have to do the inverse or the arc sine. So that's going to be A, or angle A, is equal to arc sine or inverse of 15 sine 98 over 17.5. And that's going to give us an angle equal to 58.1 degrees, and that's to the nearest tenth. So our angle that's right at A is going to be 58.1 degrees. And I'm just going to write it outside just because it'll be difficult to fit it in there. Okay, and then now when we're on example 3 here, it says determine the lengths of all unknown sides and angles. So what we're going to have to do is a multi-step process of either solving for angles first or solving for side lengths first, and then using that information to solve for the rest. So what I'm going to do is, the information we do know right away is we do know the angle of B and the side length of B, and we also know the side length of C, because according to when we do our side lengths across from our vertices, we get C is on this side, B is on this side, and A is on this side. So let's write it in the case that if we know we have enough information to solve for the angle at vertices C, what we're going to do is we're going to put it in terms of, if we go back up to our top here, it's going to be that reciprocal form where we have our sinusoidal function in the numerator and our side length in the denominator, because that's going to help us simplify this. So we know enough information to say that sine C over the side length of C is 13 is equal to sine B, and the angle at vertices B was 67 over 12. Now let's rearrange this such that we get the 13 out of the denominator here, which will help us isolate that sine C. It cancels this 13, and then we have sine C is equal to 13 times sine 67 over 12. And then finally, if we want C alone, or the angle at vertices C, we have to do the arc sine or inverse sine. So we go C is equal to arc sine of 13 sine 67 degrees over 12. And this is equal to 85.7 when rounded to the nearest tenth. And that's our degree at C. So we have 85.7 degrees here. And now remember from last problem, or even the problem before, what we need to focus on is that we need to say, well, the inner angles of the triangle should always sum up to 180 degrees. So we can actually solve for our missing angle at A, or vertices A. And so if we label this as our step 1, then our step 2 is saying, let's get that second or that third angle that exists within our triangle. So we have 180 degrees is equal to 67 degrees plus 85.7 degrees plus some unknown angle A. And so in order to get that, what we have to do is subtract both the 67 degrees and subtract the 85.7 degrees to isolate A from both sides. And thus we get A has an angle equal to, it's going to be 27.3 degrees. So now we can fill that part of the triangle in. 27.3 degrees is the A angle. And now all we're missing here is the A side length. So just to simplify a few things here, I'm going to take those out. And then, so as we can see, we have all three angles, we have two sides. Now we just need to use a sine law one more time in order to get the missing side. So let's write out as our step 3, our final component. We know we have enough information from either C or B, including their side lengths and angles, to use those in the sine law. So we can pick one of those and then pair them with the one involving A, and that should help us solve for that missing side, or specifically this side here that we're missing. So what I'm going to do is I'm going to write out, if we know we need the side length A, I'm going to write the sine law in terms of the first case. And what I mean by that is, if we know that we need a side length, let's write it as the side length in the numerator to save a few steps of algebra. So we have A over, well, sine A, the angle at vertices A is 27.3 degrees, and that's equal to, let's just use B as our calculation form. So we know we have a side length of B of 12 over sine B. Well, the angle at B vertices is 67 degrees. And so thus, when we simplify this for A, what we're going to have to do is do the same thing we've done on the other problems and get whatever is out of the denominator out of there and into the numerator on the other side. So we're going to multiply both sides by sine 27.3 degrees. That leaves us with just an A in the numerator because it cancels the denominator on this side. And thus we get A is equal to 12 times sine 27.3 degrees over sine 67 degrees. Thus, A is equal to 5.97. But what I'm going to do is just approximate this and round it to 6.0. And in terms of our units, we have 6.0 meters. So our missing side that was at the gold star, that just becomes the 6.0 meters when rounded to our nearest tenth. So thus, you can see how we've had to use a multi-step process here to solve this problem, because we had to first solve for an angle, which helped us solve for the other angles that were available. And then what we can do is use the information we have left over as a way to solve for any missing sides. So you can see how we can either do one like the previous examples, one or the other where we solve for a side or an angle, or we can technically do both in a problem if we want to solve for everything. Now finally, let's take an example 4 here, where it says sketch the triangle, then determine the measure of the indicated side. So this is going to be very much like example 1, except we have to actually draw the triangle and label all these angles. So this setup is just going to take a moment, because what we're going to have to do is we're going to have to draw this triangle from scratch. So triangle ABC, ABC being all the vertices, where angle A is 57, angle B is 73, and AB is 24. Then find AC. Okay, so this is going to be very approximate. So what we're going to do is we're going to do our 73 degrees first, which symbolizes the angle at B. So I'm just going to draw something even like somewhat near 90 degrees. So we have a line here, and then we have, let's just say that that is our 70 degrees. And then what we can do is we can just draw the rest of the triangles and just fill in any missing gaps. This is where we don't have to be super approximate. It's just important to have a triangle that's somewhat approximate with the drawings filled in correctly. So we know that we had a triangle A, B, and C, and if we knew that our 70 degree angle, we could even pick it as this bottom one here. So let's fill that in as this is B, this is A, and this is C. Thus, when we fill in what angles are at each, we said angle B is 73 degrees, angle A is 57 degrees, And then side length AB, or the ones that connect AB vertices, so this one in particular, that one is going to be the 24 centimeters. So we would write 24 centimeters. Okay. Now we have our triangle set up. What we need to do is, it's always important, if we know we have 2 degrees, let's use those 2 degrees to solve for that third degree, because oftentimes that helps us solve our problem. So in our step 1, let's say 180 degrees is going to be equal to 57 degrees plus 73 degrees plus some unknown c degree, because we don't know the angle at the vertices c. So in order to do this, what we have to do is subtract off 57 degrees, subtract off 73 degrees, and yet again we do this from both sides, because then when we isolate c, we get equal to 50 degrees. So now we can fill in that we know c is 50 degrees. Okay, now to use sine law for step 2, and to get that side length we're looking for, the side length we're looking for is actually this one here. It's the AC, the ones that connect vertices A and C. And so we have enough information on this triangle to solve for that. What I'm going to use is, we know we have an angle C and then a side length C, and we have an angle B. So let's use B and C in our sine law, and that should help us solve for this. And yet again, we can actually use the certain order as listed above. So we're looking for a side length. And if we're looking for a side length, that means we should use the first iteration of sine law, where the side length is in the numerator. Not that it'd be wrong to use the one with the reciprocal, but it's easiest and requires the fewest steps to use the one that has the missing value in the numerator. When we look at step 2 here, what we're going to say is, we're going to say, if B is the side we're missing, then we can write it as B, which is this one here, over sine. The angle at vertices B is 73 degrees, which is equal to, and then we can write 24, which is the length of C, over sine. The angle at vertices C is 50 degrees. Now, like our other problems, we have to multiply both sides by sine 73 degrees to get it out of the denominator on the side we're isolating B. Thus, we get B is equal to 24 sine 73 degrees over sine 50 degrees. And that is equal to 29.96, which we can also just approximate as 30.0, and we're in centimeters. And so this, as we've stated before, when we're looking at side lengths that connect two vertices, in this case we're looking for AC, which is this line here, it's actually symbolized by B, so we can actually rewrite this solution or equate this solution also as AC.